I'm one of the organizers for the VMV program. So it's a pleasure to welcome Professor Stacey Levine giving a talk, and she's in here briefly. So it's a bit very good opportunity. So she's going to talk about denoising geometric features of an image.
Right. Well, thank you, Cook, for the invitation. And the trip was somewhat last minute, and the seminar came about yesterday. So there's a little bit of recycling, but hopefully there's at least half of it, if not all, is new for you, and maybe you have some interesting ideas. So, so getting to it, the goal of everything I'm going to kind of speak about today is, can we improve denoising techniques? And this can honestly be generalized to other kinds of image processing tasks. It's just denoising is the easiest one to frame it in typically. Can we improve them by better taking into account local geometry? Some denoising techniques, typically variational PDE-based methods, naturally do that, but there could be certainly patch-based techniques typically do not. And so there's some interesting potential along these lines. So the general framework for really everything I'll talk about today, but I'll talk about this in several different settings, is to, instead of denoising or processing an image directly, do the following. Compute some geometric quantity of the image that somehow encodes local geometry in a meaningful way, and process that data instead. And then use that processed geometric data to reconstruct your image. And again, I'll formulate it in denoising, although this, you could easily pop that out with in-painting or super resolution. There are ways you could generalize this to other cases. The three kind of geometric measures of the image that I'll refer to today are these three: orientation matching. And what I mean by that is looking at the unit normal vector field to the level lines of the surface of an image. The curvature of the level lines, computing that directly, as well as looking at the components of the image in an orthonormal moving frame, where this moving frame encodes the geometry, again, in a meaningful kind of way. So in the second two cases, I'll go into slightly more detail about the mathematical motivation behind it, why it should work, why it should do better, and how the formulation will be expressed. In the second case, one of the benefits is there's a very nice natural extension to multi-channel images, so I'll kind of give the framework for both. I'll discuss some numerical results in both cases, and then we'll conclude. So the first work, at least that I know of, using this kind of geometric framework for image denoising, although there was some similar work on image in-painting maybe a year or two before this, is by Lysacker, Osher, and Tai back in 2004. And so in order to avoid the staircasing effect of using the kind of classical now Rudin, Osher, Fatimi, TV, total variation, L2 functional, for denoising an image and generating maybe a piecewise constant image. So to avoid staircasing, what they wanted to do was process the image surface, considering this is a surface, more directly, and in a way almost fitting a denoise surface to the noisy data in a good way. So what they did was, instead of processing U, they generated some unit normal vector field, again, using a TVL2 type functional, but with a constraint that your vector field should be normalized to 1. So compute this unit normal vector field, which should be the normal, which is hopefully the normalized gradient field to the level lines of the image surface. And then use this information to reconstruct your image. And so what they do, the way they reconstruct, is do some sort of orientation matching. So this term here forces the normalized gradient field of your solution to be parallel to the smooth unit normal vector field that you just computed, and we have our fidelity term to keep contrast. Now, mathematically, this is not the nicest problem to solve. So other work has come out of this. For example, instead of solving for the normalized or the regularized unit normal vector field, Ramantai and Osher several years later said, why not solve for the tangent field using a TV-Stokes equation? So they look for a divergence-free vector field, again using this kind of TVL2 type functional. And mathematically it's nicer. It tends to oversmooth a little bit, but it's a little nicer. So you use this tangent field to get your smooth unit normal vector field. Again, do orientation matching. There's been some work, past that on what about a better reconstruction equation? Is this necessarily the best way to use this smooth unit normal vector field? So this does kind of a feature matching. There's work by Hahn and collaborators several years ago, and there's been other things since then. Kind of a different direction coming from the Lysaker-Osher-Tai work is Bregman iterations, which is very well known at this point in the variational image processing world. And so again, instead of solving that ugly TVL2 functional for the normalized gradient direction field, just solve the Rudin-Osher-Fatemi functional, and now you have a smooth unit normal vector field you generate from that solution. And again, do your orientation matching or your surface matching. And then they made the observation that if this normalized gradient direction field came from the solution of the Rudin-Osher-Fatemi functional, which has an explicit solution. Solution of the Euler-Lagrange equation looks as such, or satisfies this relationship. It really just comes down to adding back the noise, and this was a really interesting observation. It helped preserve contrast, and they found if they iterate, they got a really nice result. So a lot of work has kind of been done in this direction. What we did was something related, but a little bit different. So we said, again, this is following the general framework on that very first slide. Compute the level line curvature of your image, which is poorly behaved, but it has a lot of rich information in it. Denoise that using some denoising method, and then generate an image such that the level lines of your kind of clean image is well described, or well described by the denoised curvature, and that the overall contrast matches the overall contrast of I. And since the average value along level lines of I should be the same as A, if we're assuming additive Gaussian noise with mean 0, this should give a decent reconstruction. And again, this was kind of intended as a general framework, so our denoising methods weren't necessarily exactly tailored to curvature information, which again is not the easiest thing to work with, but we just said, what if we just did a simple generalization of regular denoising, of existing denoising techniques? So why do this? Well, there's clearly grayscale images, which are just surfaces, can be perfectly reconstructed from their level lines. And just like a topographic map, level lines and contours can be perfectly reconstructed from their curvature information, and the curvature information is critical. So for example, in a psychology paper over 50 years ago by Etnev, he made all these interesting observations about how the information along contours is concentrated at maximum value of the curvature. That's where the interesting things happen. So if we could preserve this information, you could use it to reconstruct a nice surface. So that's all well and good, but still to actually denoise curvature is a very bizarre concept. But in fact, if you look at an image in its noisy version and look at their corresponding curvature images, the noise looks a lot higher in the regular image. And in fact, you can show analytically, this was using a discretization. We used forward-backward differences to compute the curvature, just so that we can reconstruct in a mathematically sound way. For sufficiently high noise levels, you can show that along image contours, which is really what we're aiming at, the PSNR of the curvature, the level line curvature, is strictly greater than the PSNR of the unit normal vector field, which is strictly greater than the PSNR of the image. So perhaps this might be reasonable to work with if it is less noisy. And experimentally, we looked over, I think this was averaged over the Kodak database, we looked at the histograms of the noise. So the first column, this is noise level 5, noise level 15, and standard deviation 15, and standard deviation 25 for the different noise levels. And as the noise level of the image increased, in the second row, what you see is kind of what we're calling curvature noise residual. So basically, we computed the curvature as a nonlinear operator, but if you compute the curvature of the noisy image and subtract off the curvature of the clean image, that's what we're calling the noise residual. And the standard deviation of the noise is much lower. It goes from maybe 4.9 up to standard deviation of 7 for when the corresponding images has standard deviation of 25. So this kind of looks like a reasonable way to go. So in 2014, we did some experiments, and we tried a variational approach and several patch-based approaches, applying it to this framework, and used them to denoise the curvature of the level lines of an image. Now, again, this is a nicer thing to work with because the curvature is just scalar value. So we don't have to worry about vectorial information. To reconstruct, we used a very simple reconstruction equation, which matches directly. It's just the flow of the Euler-Lagrange equation associated with the minimization problem, which is almost exactly the Lysaker-Osher-Tai functional, except maybe an integration by parts here. So to get the curvature term. So the nice thing about this is it preserves the shape of the level lines, theoretically, because at a steady state, we have that the curvature of your solution should be close to the denoised curvature, and preserves contrast in the sense that the average value along level lines of your solution should match the average value along your data. This isn't the only one, and in fact, probably not the best way. It's just coming from a PDE and variational background, it seemed like the simplest thing to do. So for example, you could look at a higher order model where you minimize the L1 difference between the curvature of your solution and the denoised curvature. And Ke and his student Carlos Brito had a nice algorithm and tried this for us, and it did work slightly better. So there's some potential for certainly other algorithms, and it doesn't necessarily have to be a variational approach. It was just what we knew best, so what we tried. And so some brief results from the original work. The first column, you see the results of comparing the variational approach. The second column is non-local means, and the third is BM3D. So these second two columns have to do with patch-based approaches. And what we did was this framework that I said, we computed the curvature, used the corresponding denoising methods to denoise the curvature, and then reconstructed. The top row is the PSNR, the increase in PSNR, and the second row is the increase in SSIM. The important thing about this is blue was the proposed framework in general. Magenta is applying these same techniques directly on the image itself. And certainly for TV, we do better, which I found really interesting because I don't see how a total variation regularizer is a good kind of prior information for curvature, but it worked. For patch-based methods, it was more challenging. And for BM3D, we got a very small increase. We saw that it worked better on the dotted line as highly textured images, and it worked better visually. But there was a small increase, and this is averaged over the Kodak database, so it was very consistent. Now this is for grayscale images, because the notion in color is a little bit harder to work with, although we did do some experiments with color afterwards, and what we did was kind of looked at this and we did this channel by channel, really simply applying to the RGB components. Not necessarily the most clever way to go about encoding the geometry, but it was simple and it worked. And we kind of looked at this as because we could do better with, for example, non-local means or BM3D, but the increment was so small, these patch-based methods are so good that why not use that information? And really what's missing is some of the geometry. Some of the level lines are just not as well preserved as you have in the variational type methods. So why not use that as your guess and then try to incorporate the geometry? So we literally just did this as kind of a boosting technique, saying start with non-local means as your initial guess. Keep that in your fidelity term. You don't want to go too far from it, but also now kind of force the level lines to be the denoise level lines. And we actually introduced more level lines, and this was an experiment by an undergraduate working with me who just saw the curvature, the noise distribution of the curvature look Laplacian, and he applied a 3x3 median filter to the curvature. So it was very simple. And then we did this reconstruction. And here, I've got to have a close-up. Again, it's subtle, but the important thing was, for example, here in the hair, you can see that when we do this kind of boosting, introducing the level lines, you get, well, I don't know, can you see it? Yeah, well, I can see. I don't know if you can see. But you get some of the lines back again. So where some of this is blurred out, it's sharpened in here. I don't know, is it visible? I don't know with the light. Oh, look at that. That was magical. There. So yeah, in this region here, we just see more of the details, and we don't really lose anything. So yeah. So it seemed to have some potential. And then we tried for several other things. For example, this is a 2D projection of 3D angiogram data. And the noise is just natural, whatever noise is in the information. And what you have in the second row is kind of a close-up with false color, so it's easy to look at. In the second row, this was an application of BM4D, which is taking BM3D in a very clever way. Maggioni and collaborators, they applied it to the whole 3D volume. So it's a 4-dimensional processing technique. And they get very nice denoising results. And then we literally took the projection and just tried to do an enhancement. Here we used a non-local means denoise version of the curvature. And so you can kind of see an example. This is what the noisy curvature looks like. But this is what happened when we denoised it with non-local means. And so you really do preserve a lot of those level lines, but you get rid of a lot of the noise in the background. And so this was the BM4D result. And this was what we got when we just did some enhancement. And we kept all of the details, but got rid of some of the oscillations in the background. And then we did a very simple experiment doing super resolution. And this was a toy experiment, but literally doing just kind of increasing by a factor of 2. So here is a high resolution image, and here is a low resolution version of it. This is what you get from bicubic interpolation, and this is what you get if you include, basically take the curvature of your low resolution image, apply non-local means to it to kind of smooth things out, regularize it a bit, and then do bicubic interpolation. So we literally interpolated the denoised curvature and the image and combined that information. And here's what bicubic interpolation looks like, and here's what we get when we incorporate curvature information, and we get more of the actual numbers and the curves. So this was the original. So it was a very toy experiment. We just wanted to see where it could go. And finally, how much can we actually do? And this is kind of an example to see some of the even some of the very good patch-based methods. And there's been more since, but it's still very good. What it loses. So here are 2 noisy images, noise level 15 and 25, and this is a close-up. These are from the Kodak database. And this is what you get, a close-up version from BM3D. And if we had an oracle and could introduce the perfect curvature back again, this is what you get. And we get this is the original image. And so we get, some of the details back again, some of the creases in the finger, the creases in the flower. So it seems like geometrically we are introducing information that was lost in these other techniques. So there are some advantages. Overall, it does seem to increase PSNR and SSIM. It does seem to introduce geometry back into some of these methods where it gets lost. So it seems like it has potential. But there's a lot of challenges. Best reconstruction mechanism is not obvious, and that ties into how you discretize the curvature, because you want to make sure that your reconstruction is mathematically sound. The discretization of the curvature itself, we're using forward-backward differences, which is not the most accurate. There's been a lot of things since then, this curvature microscope work and lots of other things. And the generalization to color is not so straightforward. We're doing a simple channel by channel, but when you're talking about geometry from color images, it's not quite as simple. So, so the final kind of framework that I want to mention is these components in an orthonormal moving frame, where the components somehow encode geometry as well. So again, the general framework is the same as on the first page. The goal is we're going to construct an orthonormal moving frame over an n-dimensional image, and you want this frame to somehow encode geometric information, or else it's not useful for this particular framework, regularize these components and project back. And again, this is formulated in any dimension, so this can be used for color images, hyperspectral images, grayscale images, any kind of dimension. So work on this, at least this is the first work that I know of, is Thomas Butard and Berthier in 2013. So what they did to regularize these components is essentially they just applied a Gaussian kernel to the components in this orthonormal moving frame. And it kind of, when they projected back, they got this somewhat Gaussian scale space that somehow encoded geometry. So that was kind of interesting. And then Butard and Bartolomeo back in 2014 said, well, what if we could make this more of a denoising technique? So instead of just applying Gaussian kernels to the components, they applied this vectorial total variation and saw that you can do better by kind of smoothing the components rather than smoothing the original image before projecting back. So then we looked at what if we can just generalize this to any denoising technique. And so why do this and why moving frames? So first is you can, the moving frames can encode geometric information in a very nice way. And there's this really nice connection with covariant derivatives, which kind of generalize differentiation, of functions. So we can look at differentiation of sections on a vector bundle and kind of has these interesting connections. More information, more rich information can be encoded in them. The reconstruction is incredibly easy because you're simply doing a projection. So to construct these components, we just apply an invertible orthonormal matrix transformation, and then just denoise project back. And again, in this case, we can show that at likely edges, the PSNR of the moving frame components are at least as big, if not greater, than the image. And experimentally, we see that as well. So here's the framework. It's not quite as simple as just generating the curvature, for example, but once the framework's laid out, it's very easy to compute. So first, the gray level case. If we have a scalar valued image, I, the idea is to encode the local geometry into some orthonormal moving frame where the first two components, Z1 and Z2, represent the steepest and the flattest slope of the surface. And so they're going to lie along the tangent plane, and N is normal to the surface. So the simplest way to do this is if we parameterize the image surface I, and we're going to look at a scaled version of the image surface, and actually that scaling parameter is important to actually make this work. But just a simple scaling parameter, we kind of attenuate the surface. We embed the image in a three-dimensional surface, a three-dimensional vector, and then take our Z1 and Z2 to be the normalized directional derivatives in the direction of the gradient and the level lines, which seems like the natural thing to do. If there's locations where the image is flat, we just take Z1 and Z2 to be the standard unit normal vectors. And again, mu can be kind of viewed as a smoothing parameter, and it is kind of important. It makes a difference in the actual solution. So Thomas had made a very nice picture illustrating this. So this is a simple cone represented as an image in a surface. Your Z1 and Z2 point in the gradient and level line directions, and N is normal to the surface. So the grayscale case is fairly straightforward. Again, the nice thing about formulating it in this way is the frame change field has a nice explicit form. You can compute the components very simply, and in fact the middle component ends up just being 0. So we really only have two components to process. And these components are a combination of the image data and the gradient, magnitude of the gradient. And it's kind of interesting how they decompose the image. So what you see here on the left is the original image. Here's J1 and here's J3. So J1 is the image data kind of scaled by this ratio of the magnitude of the gradient. So where the gradient is very low, where the image is flat, J1 is 0. Where the gradient is high, J1 takes the intensity value of the image. So we end up with something that looks almost like a map of the edges and textures. J3, this is an I here, not a 1, is I, the image, divided by kind of an edge detector. So what happens is it looks very similar to I in most regions except where the gradient is very large, which is at likely edges, and then it looks like it's almost zeroed out. So it's almost like we're separating the textures and the edges from all the other information. So it turns out that, again, and this turns out, well, I think we can actually find a better bound on this, but we have that the point signal to noise ratio of J1 and J3 are always at least as big as the point signal to noise ratio of the original image I. However, this is only the case if we do attenuate the image. So for example, when mu equals 1, when you have just the original image, this is experimentally speaking, has higher PSNR. So we need to have mu strictly less than 1. And in that case, for example, once mu hits 0.01, J1 and J3 have, fairly equal to significantly higher PSNR. So in some ways, maybe they're nicer to process. Okay, so for grayscale denoising, the general framework is now pretty straightforward. We compute the components by doing a simple projection, denoise the components, and then apply the inverse frame change matrix. Now, technically, theoretically, the first two components should be 0, so the denoised image is just the third component. In the multi-channel case, we have to be a little bit more careful because, unlike the gray level case, you don't necessarily have level lines. So you don't have the same interpretation. And there's also many choices for the normals to the surface, the vector field of normals. But we still want that Z1 and Z2, the first two, point in the direction of steepest and flattest slope. So the most natural thing to do is to take Z1 and Z2 to be the normalized derivatives in the direction of the eigenvectors of the metric tensor associated with this image surface. And then just apply Gram-Schmidt to get the remaining normal vectors to the surface. And now we have, for an n-dimensional image, we'll have n plus 2 moving frame components. And that's the representation of the image in this n plus 2 dimensional frame. So that's the whole framework. So there's some flexibility. So even for grayscale images, and certainly up to multi-channel images, when you're working with frame components, we now have vector valued images. So we can process this vectorially, all the channels together. We can process it channel-wise, or we might only want to process selected channels. And depending on the approach, there's different ways we went about this. And there's also some flexibility in choosing the color space, which is always a consideration when working with color images. So for the variational approach, the most natural thing, we kind of to keep in the ROF framework, because it was a simple framework to work in, is to do a vectorial extension of the Rudin-Osher-Fatemi functional. So this is the vectorial total variation of Bresson and Chan. And so what we did was we applied the vectorial total variation to the image, and then also did the same experiment by computing the components in the moving frame, applying VTV there, and projecting back. And again, on gray level images, this is just a simple ROF functional. Excuse me. So the so the moving frame approach is exactly as I said before. In this particular case, J1 through J3, once you compute the components, they're processed kind of in tandem with each other. So VTV, for the vectorial total variation, the channels communicate, so they play into each other. We get the denoised components, project back. The last component is our denoised image. For color, we did the same thing, except now you embed your three-dimensional image into a five-dimensional, well, not embed, you project it into a five-dimensional space. Denoise this vectorially, just in n plus 2 equals 5 here. apply the inverse transform, and the last three components are your processed color image. So here's some results with the variational approach. We have an improvement in terms of PSNR, that's the first comparison here, and SSIM, both for gray level and for color. It's not huge in all cases, but it's consistent. And this is, again, averaged. We did all the experiments averaged over the Kodak database for consistency. And here's what it looks like, which is perhaps, you know, again, we have these increases, although PSNR and SSIM only tell us so much. But this is what the actual visual image looks like. So the first column is the noisy image. The top you see the image, the bottom you see a close-up. The second column is VTV applied to the image. And the last column is doing VTV applied to the moving frame components. And so here is a even closer close-up. You see, you know, we get sharp edges, which you would expect from a TV L2 type functional. And this is VTV applied to the original image, and this is what you get when you apply it to the moving frame components. So the significant thing is you really do get more details, more, in this case, more textures, which is often kind of what we saw, that it works very well for highly textured images. So now, non-local means. For non-local means, again, for the grayscale case, it was still fairly straightforward. We computed the moving frame components. In this case, we computed the NL means algorithm channel-wise, because vectorial non-local means isn't quite as, there's not as many approaches, and that was a simple thing to do. We approached it, we applied it channel-wise, projected back, and the third component was our denoised image. We used the default parameters in IPOL for the which depend just on the noise variance. And the only other thing that the NL means is parameterized by is this mu. And in our experiments, though, we actually took mu to be the same for all of them. So the best results came from working in this color space used in the original BM3D paper, which I'm not sure why we call it AOP, but the main important thing is the first component encodes luminance information, and the second two encode chrominance information. So when we're working in color, really the luminance information, the intensity information, is the most important when we're trying to preserve geometry. The chrominance, not so much. So the upshot of all this says the luminance component that we're going to process using the grayscale moving frame approach. The other two we could just apply non-local means. The geometry isn't doing much for us. And then reconstruct and project back into RGB. And here are the results. Again, this is averaged over the database. Again, we have a very slight increase, but it's consistent for PSNR and SSIM, both for the grayscale and the color case. But here the details, again, are kind of, that's where the important thing is. This is the same thing. We have a noisy image. This is non-local means. This is the vectorial, this is the moving frame approach with non-local means. And so here's what you get with non-local means, and here are the moves, but here are the details when using the moving frame approach. So again, that's non-local means, and here we get more of the dirt, etc. The BM3D framework, we did exactly the same way as non-local means. We processed it channel by channel for the grayscale case, and in the color case, we projected it into a color space where you have a luminance channel and two chrominance channels, and only really process the luminance channel with the moving frame approach. And we have a very slight increase. It's consistent, but very, very slight. But the PSNR increase could kind of echo these optimal denoising bounds that have kind of been studied since 2010, Chatterjee and Malanfar, and Levine and Nadler, where they said you're just not going to do much better, maybe 0.1 dB of BM3D directly. Although people have done much better than that, and that's what they said. But PSNR, you know, again, there are some limitations using that for a measure of goodness, even SSIM. But what we do see here, again, noisy image, BM3D, And the last column is the BM3D with the moving framework. And if we look at a close-up version, here's BM3D, and here is, and this is pretty subtle, but it's there, BM3D in the moving framework. So where you can really see it is in the textures, well, at least where I see mostly in the textures and these slats and the plants, and here we get more of the textures. So, kind of to conclude, just these approaches that I showed, it seems that this general approach of maybe computing some geometric feature of an image, denoising it, and then using that to reconstruct seems to have potential. And it could have potential for other processing techniques as well. It improves generally on PSNR and SSIM. Where I think maybe it's more interesting is that we do kind of reintroduce these level lines to some of these patch-based methods, and perhaps now that there's CNNs and things, we haven't even looked at any of that. I don't know how it does with preserving geometry and such, if there would be any improvement, but certainly with the patch-based methods. And then the moving frame components have the benefit that it is very easy to compute. It's very easy to reconstruct. There's just an obvious linear transformation both ways, and it's very simple to extend to the multi-channel case. The curvature has the benefit of the results are actually slightly better. We do get a slightly more geometry. So, and there could be other measures that would work even better. And there are some things currently that are kind of questions out there, some of them that we're working on. Most recently, we were kind of looking at kind of extending that curvature denoising framework to Bregman iterations. So instead of just adding back the noise, essentially it comes down to adding back the noise and the curvature residual and doing this curvature matching. And what we found so far is that it does increase over Bregman. You get a pretty significant increase, in fact. And visually, you do see the geometric features, but there's still this work in progress. We'll see how it ends up. But so far, it looks promising. And then there's so many questions that have to do with this framework if these were to be extended further. For example, a better way to denoise, for example, curvature. Is there a prior you could put on it? It seems to have Laplacian noise. We haven't even been, except for my student who tried a median filter, we haven't done anything about that. So is there a better way to, could you use some learning technique? Is it easier to learn geometry than to learn the original image? It seems crazy that it would be easier to learn geometry, but it is sparser. You know, curvature is like somewhat of a sparse thing. Like think about the curvature of a square. It's really 4 ugly points. Could be. It seems less noisy, so perhaps that's helpful. A more accurate reconstruction equation, which also ties into the discretization of the curvature, which ties into how you're regularizing it, understanding the best color space and what framework to work in. And the moving frame components, again, we just took existing denoising methods, and maybe that's the benefit of this, and maybe, but maybe there is some way to do this more intelligently, since the moving frame components decompose the image into geometric features in a way, the edges and textures in J1 and everything else in J3. So would you treat these differently? Could you denoise them better than just applying existing techniques? And I had to throw that in there. Is there anything we could learn? Because I think I'm pretty sure that's everything has to be connected to deep learning somehow if there's anything interesting to be had. So maybe that's tongue-in-cheek, maybe not. But I don't know. The curvature is kind of like the residual of the Rudinow-Shepardini functional. And there's all these like residual learning techniques. So maybe there, I don't know. But big questions. But thank you for your attention and for the last-minute invitation. And, that's all.
Thank you. Do you try the 2 other noise types?
No. And there's no reason that we can't. We just haven't. But yeah, it very well might have. It might be easier to work with other noise types than Gaussian noise. Yeah. Mm-hmm.
What is the overall error of the methods? Which means you don't put any noise, then just run this, then look at the PSNR in average. That will give you the error of the method.
So
Because you have
use the
a
reconstruction.
database to run, so this gave you an idea.
I haven't done that, but that's interesting. So you're saying like run this like for the moving frame, which is
Whatever without any noise. Just take the original picture in and write.
and then for
And see
example,
the PSNR with the original and see what's part are altered or something.
well, I think that the moving frame should be pretty easy since it's just a transformation back and forth. That should be good. It shouldn't have too much error. I think the curvature very well would have. Yeah, but I haven't checked. Interesting. Mhm.
Thank you.